Welcome, and thank you for joining this webinar, Invisible Power, Infinite Scale, How Ambient Energy is Pushing the Battery-Free IoT World, prepared by Alpert Research team. Starting with the fuel for all of this, ambient energy harvesting.
So ambient energy harvesting, or EH, is just a process of converting energy that's already around us, light, heat, motion, radio waves, into usable electricity.
And the whole system has to be built around the idea that this power source is unreliable.
Completely. It's intermittent and unpredictable. That's the key difference from a battery. How do we judge the efficiency and, I guess, the viability of any given harvesting solution?
We use three key performance indicators, or KPIs, to measure success. First is power density. It measures the achievable energy output relative to the size or volume of the transducer. For AIoT, we need high power density to achieve that tiny 1 millimeter squared form factor. The second KPI is conversion efficiency, which is the percentage of incident ambient energy that the transducer successfully converts into usable electricity. And third is dynamic range. This is the spectrum of input energy levels over which the conversion efficiency remains effective. A wide dynamic range is essential for any practical deployment. Most AIoT devices fall into two categories defined by their energy buffer. So batteryless devices rely purely on small capacitors, ranging from microfarads to millifarads to buffer energy. These are the extremely small, low-cost tags. The second type uses limited energy storage, like supercapacitors or highly miniaturized thin-film batteries, specifically to handle energy spikes or longer burst tasks. Well, the CSC tick all the boxes for the AIoT mandate. They're low cost, they offer an excellent cycle life. We're talking millions of charge-discharge cycles versus thousands for chemical batteries. And they are maintenance-free and far more eco-friendly. They enable that critical miniaturization we need.
This intermittent energy supply leads directly to the core operational behavior, the ONO-F states. Walk us through the mechanics of a typical power cycle.
It's a cyclical process, and it's managed by the Power Management Unit, or PMU. So the capacitor starts charging when ambient energy is available. The device only powers on when the capacitor voltage reaches a high threshold, which we call V on. It then attempts to execute a task. If the task is long or the ambient energy vanishes, the voltage drops. Once it hits a lower threshold, V off, the PMU abruptly switches the device to prevent permanent damage to the electronics. It must then wait for the capacitor to recharge back up to V on before it can resume.
And this abrupt switching means tasks are interrupted constantly. This is the unavoidable problem of intermittent computing. If I'm halfway through encrypting a sensor reading and the light source vanishes, what happens to that work?
That computation work is just wasted unless you employ an interruption-tolerant mechanism. The primary solution is something called checkpointing. Since system shutdowns are unavoidable, the computation itself needs to be designed to resume gracefully.
So how does this state saving work in practice?
The key is saving only a minimal high-level context to non-volatile memory just before that brownout occurs. You can't save the entire state of the CPU registers. That would take way too much power. This process has to be highly efficient. And while it does introduce an energy overhead, typically around 10% of the operation time, it prevents the complete waste of energy.
That 10% overhead is a critical design trade-off. It costs energy to save energy.
Exactly. It's an essential compromise you have to make. That intermittent nature means the system can't be dumb. It has to manage that energy.
Think of it as a continuous power management loop that every AIoT device has to run. It starts with phase one, availability assessment.
Figuring out what energy is even there to be harvested.
Precisely. The device has to check what sources are present, how strong they are, and how they change over time.
Okay, phase two.
Energy conversion optimization. This is the engineering magic. You've got the right harvester, you're matching the impedance, and this is critical, you're using something called maximum power point tracking, MPPT.
Which is an algorithm that squeezes every last drop of power out of the source.
That's a perfect way to put it. It constantly adjusts to make sure the harvester is operating at its absolute peak efficiency, even as the light flickers or the vibration changes.
Phase three must be about storage.
It is. Energy storage and management. Because the energy is a variable, you need a buffer. So the system routes the harvested power to those CSCs, the supercapacitors, to save up for a quick burst of activity.
And the final piece of the puzzle.
Energy consumption optimization. This is the other side of the coin. You have to minimize what you use. We're talking about electronics with standby currents in the nano-amp range and really aggressive duty cycling. The device is asleep almost its entire life.
Harvest use versus harvest store use. Why can't these devices just harvest and communicate at the same time? It seems inefficient to have to stop and charge up.
If the ambient energy is really weak or spotty, you have to use what's called sequential harvest then consume, or SHC.
So you disconnect everything else while you're charging?
You disconnect load the brain of the device, the radio. You do that to maximize the efficiency of accumulation. Even an ultra-low power chip draws some current. By disconnecting it, you ensure every single microjoule you harvest goes straight into charging that capacitor.
And only then, when it's full enough.
Only when the voltage hits a specific threshold does the device wake up, do its job in a super fast burst, and then immediately go back to sleep. That sequential approach is what guarantees you can actually complete the task. I think the key strategic takeaway is that shift in market dynamics. This technology fundamentally transforms what used to be an operational cost for a network operator, blasting out a radio signal, into a monetizable service, providing wireless power. This movement creates new ecosystems where the manufacturers and retailers who actually own the sensor data become the new data hubs. They create value in a way that's separate from just providing connectivity. It forces a total reassessment of where value lies in the entire IoT chain. Interested in gaining a deeper understanding of the transformative power of wireless technology? Join the Alpert Research team's webinars to explore cutting-edge wireless innovations, their applications, and their implications. Click the links below to learn more.